And welcome to the Daily Space Weather. We've been talking about filaments here in the Smash News Network, least busted name in news. You may have seen a video that we put out yesterday featuring an incredible crown prominence up in the northwestern limb of the closest star. We'll be talking filaments and lots more on today's Daily Space Weather. So thanks for tuning in. And congratulations on realizing that the channel exists. Let's take a look at this crown prominence that you may see collapsing up here. Part of it's collapsing, part of it has ejected into the greater solar system. So you may see some plasma splashing back down toward the chromosphere here and creating some supplementary flaring there. A common feature when plasma filaments do collapse. You see those little brightening areas there? As part of that plasma filament makes it back down. That's called the Andrea-Ghez solar filament. Here's some great imagery of that. Both the coronal mass ejection and the collapse. So great stuff there. And let's go around the horn since there are still plenty of additional filaments. Part of that one is still intact also. Huge filaments here around the western limb. As those regions set, we still do have a couple of rather large sunspots, one which will get a name today. We'll cover it right after we talk about coronal holes. Here's the southwestern limb, and we've got some very well-defined coronal holes, and we can expect some significant space weather from those, perhaps even some mid-latitude aurorae, as we've got some quite well-defined coronal holes showing up here, rotating in from the west. They are of south polar magnetic orientation. Check it out. Another prominence showing up down here as a new filament forms. Around the southern crown region, we're getting a southern crown prominence now. Here's the northeastern limb. And that new sunspot is right here. Again, we'll talk about that in a moment. And the biggest filament, one of the biggest ones we've ever covered on the channel, is actually this filament right here. I mean, look at the size of that thing. That is a gigantic filament indeed, encircling part of the north solar polar region. Let's take a look at sunspots briefly here. The SDO intensity gram from yesterday plus today. There's the colorized magnetogram. And we'll take a close look at that new sunspot a little bit later in the video. So Santiaguito has been erupting. We'll take a moment here to look at Crescent Earth. Santiaguito there, producing some new real estate, volcanic ash, etc. Let's check the list and see what else has been going off. So, starting out with Semeru here in East Java, it's producing a 14,000-foot ash plume as it explodes. Flight level 140 over East Java from Semeru. Flight level 220, a 22,000-foot ash plume over central Mexico from Popocatépetl. Santiaguito is located in Guatemala. It extruded some lava as well as exploded. Flight level 150 over Santiaguito. Fuego also in Guatemala, also exploding. Flight level 160. Revenador has dispersed its ash over Ecuador, fertilizing the countryside, and Sabancaya unable to detect. Don't assume it's not erupting. By the way, today's featured product is Because Reasons. So why is mankind trying to destroy itself at least since 2020 in earnest? Because reasons. Why is your content censored on the internet? Because reasons. Why hasn't Twitter eliminated shadow bans and other deboosting features? Because reasons. Why is there zero accountability in a banana republic and rampant corporatism and corruption? Because reasons. Anyway, that's our latest design. You get the basic idea. It features an intercontinental nuclear ballistic missile launch. That's a Minuteman III if you're wondering which one. Also a hypodermic needle, a flaming planet Earth, a mask, a CDC logo, and of course this object up here, which will remain unnamed. Let's take a look at earthquakes. Here's the past 90 days. It's been pretty calm over the past 24 hours on planet Earth. Only a few quakes, a couple of quakes here, I think. Only like 2 or 3 in a 5+ magnitude. Let's go up the list. There was a 5.4 off the coast of Central America. That was at 10:55 Universal Time yesterday. A couple minor quakes there around California once again. Tonga had a 5.3. That was at 6:18 this morning on April 21st. And the largest quake of the past 24 was a 5.8 in the mid-Indian Ridge. There you go. That was at 9:06 this morning. And let's get back to space. Here's the past 24 hours in the ever-popular SDO 171 angstroms wavelength. Good stuff. And here we've added 211 angstroms, which will show the extended corona, as well as highlight those very well-defined trans-equatorial coronal holes. So I avert your attention to this location. That is a very well-defined coronal hole. It'll become more and more well-defined as it rotates closer and closer to Earth. And we can expect some space weather coming from that. And let's see what else is going on in terms of the stats. 10.7 centimeter radio flux is now at 147 solar flux units. If you're not familiar with the radio flux, it's a radio signal that comes out of the upper chromosphere and lower corona, right about where my pointer is. It was discovered in 1947 by Canadian radio enthusiasts playing around with some World War II equipment, realized that the radio flux is kind of important. It's the emissions from the hydrogen there, and that radio flux increases with the sunspot number, which is what you're looking at here. This is a 1-year graph featuring the sunspot number as a red line and the 10.7 centimeter radio flux as a black line. It is a directly proportional statistic to the sunspot number. When you see a high sunspot number, you see a high radio flux, and vice versa for the troughs. Again, 147 solar flux units. A solar flux unit is 10,000 Jansky. And a Jansky, if you're wondering what that unit is, that's a measurement of radiation traveling through space. Anyway, here is the NOAA forecast. No geomagnetic storms or geomagnetic unrest in the forecast here by NOAA. We did see a little bit of activity. We'll cover that here in a moment. First Earth magnetic moment from space for the past 4 hours. You see some variations in the solar wind happening there. That one about 3.5 hours ago. See a rapid increase there, and then a big puffing out of the magnetosphere, perhaps. This model is based on the space weather modeling framework. If you want to read about the variables used to calculate this, magnetohydrodynamic pressure, click on Details, this tab down here in the lower left. Click the Details tab. It'll link you to the space weather modeling framework. Here's Earth's magnetic moment from the ground. See a little significant pulse happening there. It'll probably be reflected in something like the solar wind data, perhaps a variation in the magnetic field or in the solar wind density or speed. We'll cover it. This is the past 4 hours of Earth's magnetic moment from the ground. Everything's looking pretty steady there. Earth's magnetic fields are not looking like they're going to reverse anytime soon, like during your lifetime. During the next 1,000 years? Anyway, the KP index is currently at 1.66. It's an average of global geomagnetism. The planetary K index, KP 1.67, is the current state of geomagnetism, geomagnetically calm conditions. Next, we'll look at the real-time solar wind, which is measured outside Earth's magnetosphere, out here at Lagrangian point 1, about 1/93rd of the way to the sun, about 1 million miles away. So what we saw here most likely was this shift in the BZ. That little shift there in the BZ was sufficient to create those pulses. So those negative BZ signals there, that could have been all that caused that. Let's see, that's about 3 hours ago. As that creates more induced current in the Earth system, basically it pulls material in, creating current. when you have a negative BZ. That's this top line here. That's the vertical component of Earth's magnetic field. The white line is the total field. The red line is the vertical component. And again, when you see a strong negative BZ, which is the red line, then that greatly increases the propensity for geomagnetic storms and geomagnetic unrest. Current conditions are about 370 kilometers per second for the solar wind speed, about 4.3 protons per cubic centimeter for the solar wind density. It's pretty diffuse and pretty slow at the moment. GOES magnetometers here broke into a much larger range. There are the readings from those for the past 3 days. Recent dip in the GOES magnetometers. And the GOES 18 there, which is the blue line featuring an arc jet moment where it turns on its thrusters in order to maintain its geosynchronous near equatorial orbit. Next, we'll look at the heliospheric current sheet. So moving out of the earthly magnetism, which is what the GOES magnetometers are measuring, from there, about 23,500 mile altitude orbit. These data are based on ground-based observatories, 51 ground-based ones, as well as on stereo A right here and stereo B over here. And Earth is just in a south pole current sheet here at the moment. No changes expected anytime soon for that. Again, we do have a new sunspot in the southeastern quadrant. We'll show you that here in a minute. First, our line of sight field plot. You can see the sun's B field there fanning out as Earth approaches the middle of the South Pole-oriented current sheet depicted there in red. And let's move to coronal holes. We've got all South Pole-oriented coronal holes here. So let's show the latest image of that. There's the last image there. And here's a great wavelength to view coronal holes, 211 angstroms from the SDO. That's a 24-hour video. So we expect this to be quite a geo-effective coronal hole indeed. Transequatorial ones are the most geo-effective. And coronal holes are the source of high-speed solar winds. So there are protons blasting out of those coronal holes as the sun creates a giant spiral of plasma. Let's move to sunspots next. We're going from the corona to the photosphere. All right, so here's some photosphere analysis. And we'll have at least one new named sunspot, 3285. That'll be this new group. It is certainly beta gamma class. And the most likely places to see large flares are currently, let me draw it over here. The most likely places to see large flares would be from 3282 and from 3285 down here in the southeast. So the southeast and the northwest are the most likely places to see large flares. Here are sunspots. We've put the 94 angstroms wavelength here along with our SDO continuum just to highlight active regions. A bunch of active regions there in the south, a large one in the north. These are 24-hour videos also, and there you go. Most of those sunspot groups quite stable over the past 24 hours, no major changes. And one of our viewers have determined that the sun is saying cameo. I can't type. All right, anyway. Cameo is what this says. It's a C and then some letters and then an O. C-A-M-E-O. I don't know why. Maybe the sun's going to make a cameo in your favorite disaster movie and destroy. Maybe the sun's going to turn into a black hole and destroy the entire universe. Are you spooked? Let's move to energetic particles and solar flares. No solar energetic particle events. The proton flux remains flatlined for an extended period here. And sunspots have really been underperforming as far as flares go. We've seen the flare profile dropping. So we saw it come up and then drop back down into the B level background. We're currently at about a B7 background X-ray output. And here's a good wavelength to view solar flares when significant ones happen, which they haven't for quite a while here. 131 angstroms from the SDO. It takes 10 images per minute instead of only 2. So that's pretty sweet. And let's take a step back here before we go to things like coronal mass ejections, because we've had some rather spectacular ones in the past 24 hours. So let's check it out. But first, see what's going on overhead. So here's skyandtelescope.org's star chart. The sun just peeking over the horizon here at Lehigh Valley, Pennsylvania. Jupiter heralding the sunrise each morning. At the moment, if you're up before dawn, you might see that bright object there. It's currently the 5th brightest object after the sun, the moon, Venus, and Mars. Jupiter rising ahead of the sun. Also Saturn. If you're up a lot earlier than that, you might see Saturn. Next, your solar system forecast. We hope you enjoyed the new moon, all you reverse werewolves out there. And here is your solar system forecast. And by the way, I've got some words of encouragement right here. Here's what you should do. And here's... Okay, I said nothing. Here's your 1-week forecast for the solar system, as this side of the solar system is getting a little bit less lonely here as Mercury and Venus are making their way around. There's where things will be in a week. And let's move on to our coronagraphs. So here's the Soho-Lasco C2. This is from George Mason University, and there's that coronal mass ejection. That's the Andrea Ghez filament. This one up here, right there. There goes the Andrea Ghez filament. Part of that is still intact, actually. So part of that ejected, part of it splashed back down toward the chromosphere, and part of it remains a filament, or in this case, a prominence, as it's hanging off of the polar region rim. So that's 107 frames from yesterday. Here are additional 31 frames from today. CME happening right there at the end from the east. All right. And let's take a look at the view from Stereo A and Soho-Lasco C3. So here's Stereo A over on the left, Soho-Lasco C3 on the right. By the way, that most recent CME does not appear to be earthly directed either. It looks like it's off to the west. And we'll let these play through. By the way, that's Mercury showing up on the Stereo A coronagraph. Your screen left, Mercury there making an appearance. All right, we've got some more custom imagery here of coronagraphs for you. These are 24-hour videos. Here you can see the Andrea Ghez filament ejecting in the north. There's an even closer view. And here's a full disk view in the 193 angstroms wavelength. And let's talk filaments, because it remains the story. Filaments. There are a lot of them on the Earth-facing portion of the solar disk. And once again, I sound like a broken record. If you want to name filaments after living people, join us over on Twitter. Follow the hashtag #NameThatFilament. And you too can name filaments. So this one's already named. But we've got at least 1, 2, 3, 4, 5, 6, 7. I'll say 8 filaments that could be named. We We don't usually name them when they're this far over to the west because they're going to rotate out soon. But yeah, lots of filaments to name there. Again, follow us over on Twitter, hashtag #NameThatFilament. We are all over the internet at Smashomash. So join us on social media if you haven't completely unplugged. And if you have completely unplugged, we don't blame you because the state of affairs on the internet in general is utter crap. Utter crap. As a bunch of ultra-rich celebrities are promoted, parroting a bunch of stale, boring, dated ideas, just saying the same crap over and over again, the same pathetic talking points, zero nuanced stance on anything. That is the state of affairs on social media. Everybody is in their tribes spouting completely closed-minded garbage on the internet. So that's the past 24 hours. There's STO 131 plus 171. Great at showing plasma orienting to magnetic field lines. If those look like your high school science experiment showing iron filings on a magnet, well, those are iron. Those are the emissions of specific species of iron in the extreme ultraviolet spectrum. So here are the past couple of hours. We still indeed do have a massive prominence over there in the west. So there's a great trans-equatorial prominence, and also this southern crown prominence forming. And thanks for leaving a comment, Mr. La Follette. This brings us to our bonus feature segment. Let's blast through some additional space weather, like our space weather satellites community dashboard here. It's going to show charging hazards, and it doesn't show any at the moment because it's clear sailing for satellites. Here are the GOES electron flux data measured using radiography by the GOES 16 and GOES 18. They measure it at the F layer of the ionosphere. More on the atmospheric layers as we transition to our meteorology segment. But first, additional bonus features. Here's the NOAA forecast, expecting a slight dip and then a slight increase in the electron flux. No arguments from me there. We'll have to see what happens on that one. The green boxes of the forecast. The yellow diamonds are talc. No, the yellow diamonds are the observation. Here's the one-year graph to put that in context, and we are in an electron deficit trough here, as you can see. The relativistic electrons here at low levels for an extended period. And if that scares you, if you're spooked by low electron flux, let us know in the comments. No, it does not mean that we are in a grand solar minimum. So here's the F layer of the ionosphere. And again, we're going to talk about atmospheric layers here and temperatures. If you are unfamiliar with the temperature structure and the penetration of electromagnetic radiation and so on, feel free to pause the video on this frame. Here is the F layer of the ionosphere. And we are seeing significant anomalies once again showing up in the ionosphere. So this is the raw vibrational frequency in megahertz, millions of vibrations per second. This data courtesy of Australian Government Bureau of Meteorology, and we'll show the anomalygram also, as it may be a little confusing looking at the ionogram. This is the anomaly in megahertz from the 30-day median. Now keep in mind this does change with the seasons. So, of course, the ionosphere is under a different environment around the equinoxes than it is around the solstices because of things like the Russell-McLaren effect, which excites relativistic electrons in the outer Van Allen belt, and that changes the vibrational frequencies there of the layers beneath that. But it's pretty hard to tie all of those different layers together, as we're only able to look at one slice of things at a time, and of course it's a little complex in terms of what's going on in the different layers of the atmosphere. Anyway, this is your anomalygram showing high frequency anomaly in blue, low frequency anomaly in red. And I would note that we are seeing some major anomalies, especially around these areas. Now, that might not be of any surprise to our regular viewers, as we have the South Atlantic anomaly now over the South American continent and the South African anomaly over Western Equatorial Africa. So those are the weakest spots in the ionosphere, but we are seeing some major anomalies sort of centered around those regions. There's the latest image, 1030 Universal Time Ionogram and 1030 Universal Time Anomalygram. Will also show the total electron content. That is the free electrons from your GPS satellite down to your handset, a run of about 12,500 miles. Feel free to pause the video on this frame if you're unfamiliar with distances to these sort of things in miles. Here's the coupled thermosphere, ionosphere, plasmasphere electrodynamics model, depicting the most likely places to see GPS errors. We are seeing some GPS errors here far away from the equator, which is typical of times of low electron flux. We've covered it for years and years on the channel. It is an obvious correlation. Low electron flux is associated with less organized total electron contents. Again, that is the free electrons from the inner portion of the outer Van Allen belt, the outer plasmasphere, the inner Van Allen belt, the inner plasmasphere, and the ionosphere. Those can be a lot of electrons, which cause GPS errors. We'll close out our space weather section with analysis of this new sunspot. There are the fields. It is a beta-gamma class sunspot. Looks like a little delta showing up here also. So I'll say it's beta-gamma delta class. That's a good thing. If you are hoping for things like solar flares and coronal mass ejections, as we are on the channel. And if you're frightened of this, I don't know what to tell you other than that the sun isn't going to kill you. Maybe if you're an astronaut, or maybe if you're doing transpolar flights all the time because you're a commercial airline pilot. However, the cosmic ray flux is really the issue there anyway. And thanks for leaving a comment, General Disturbance. Time to move to our meteorology segment. And before we do that, I just want to take a brief moment to talk about the temperatures of the layers of the atmosphere. So, a lot of people may not be aware of this. The troposphere is warm at the surface. The lower troposphere, right? That's the part where all your weather occurs. It only goes to about 10 kilometers of altitude. It's warmer at the surface and cold at the top. As you may have noticed, if you climb a mountain, it tends to be colder at the top of the mountain. However, once you get to the stratosphere, guess what happens? The temperature goes from cold to hot. As you get up to about 50 kilometers, the stratopause, where the stratosphere becomes the mesosphere, and then temperature drops back down from the bottom to the top of the mesosphere, and then temperature goes back up once you get to the thermosphere. So the thermosphere is really the bridge between Earth and space, and as you go higher and higher, you tangentially get higher and higher temperatures as the particles are more diffuse. However, they're also hotter. So just so you are aware of that, the atmosphere is quite a complex system, and just so you're aware of that, it's there are quite a bit of complexities going on up there. And if you're wondering about X-rays, the X-rays are done by the time they get to the mesosphere. The mesosphere prevents X-rays from making it to the stratosphere level. And this is why we must measure X-rays from space. They do not make it to the ground level. And let's talk about pressure. So now we're looking at mean sea level pressure. That mean sea level pressure. And at the moment, the North Pole is featuring some high pressure. Now I want you to do a little thought experiment here. Imagine pressing your hand into a kiddie pool, right? Now imagine the Earth is a kiddie pool. You're going to press your hand right into this area, right? Here's your hand, your giant hand. And you're pressing down here, right? Now what is that going to do? That's going to create a high pressure zone. It's going to create a high pressure zone under your hand. But what's it also going to do? It's going to create low pressure eddies around where you're pressing your hand down into the kiddie pool. You see this? So this is a prime example of a high-pressure system, a very huge high-pressure system, surrounded by smaller lows. Now again, just visualize pressing your hand into a kiddie pool. The area under your hand as you press down is going to have higher pressure, and the areas around it will have lower pressure as it tries to reach static equilibrium. Static equilibrium is what everything in nature is trying to achieve. And I just wanted to just show this briefly for that little brief thought experiment there. Now keep in mind, this is all the lower level atmosphere. So you're seeing the animation here is surface winds, and the coloration is the mean sea level pressure, the average sea level pressure for that area. Maybe that helps a little bit with your understanding of atmospheric physics. Here's a prime example of it happening around Antarctica also. You can see high pressure there, surrounded by low pressure. And of course, it's a little more complex than that, but that is some basic physics about reaching static equilibrium with respect to high pressure versus low pressure systems. Anyway, let's switch to our standard issue surface winds of the eastern world. There you have those. It's pretty windy on the east coast of Australia. Shout out to Kimberly. Here are the jet streams of the eastern world. Jet streams of the western world depicted here. Tripled up jet stream over the Atlantic Ocean, at least the northern part. Surface winds of the Americas. Still very windy in the northern Atlantic as well. Surface winds of the central world depicted here. And last but not least, the jet streams of Europe, Africa, and the Middle East. By the way, thanks for tuning into the Smash News Network, least busted name in news. Let's move on to take a look at clouds and fog over the western world. Here's our 3.9 micrometer radiation map showing infrared radiation emitted from clouds and fog. It's too dark over most of that map. However, the shortwave radiation map works at nighttime. So if you do see the aurora, if you do see a forecast for aurora, this will help you out. The NASA GOES Interactive Weather Satellite Suite. It's the 3.9 micrometer radiation map. And let's take a look at our weather.gov map for the U.S. as we zoom in. So that's what's going on. It looks like we've got some hard freeze warnings in the center of the country. If your location is lit, click your location. We've scrolled down to show you the key. That's about all we can do. We've got severe weather around Galveston, the Gulf Coast of Texas here, getting some severe weather. Again, weather.gov. If your location is lit, click your location. And here comes a forecast. So normally we would have this already queued up, but we're coming at you a little earlier today, so we're going to have to create some forecasts on the fly. Here's your 72-hour GFS pressure and precipitation forecast as moisture sweeps toward the east. Again, that's a 72-hour GFS pressure and precipitation forecast. Additional severe weather here expected to pop up once again from southern Texas. And since we've got some snow in the forecast, let's also show that. So we'll bring up the same model here, the 72-hour positive accumulated snow depth change in inches. So there you go, the Rockies expected to get some snow, as well as the Dakotas, Minnesota, and Wisconsin. Anyway, once again, there's the 72-hour pressure and precipitation forecast. There is the accumulated positive snow depth change in inches forecast. And let's move on to look at precipitation type. And it's snowing in Idaho and Washington and Oregon, even parts of Utah getting a little bit of snow there. Also the Dakotas, Montana, Wyoming, and Minnesota seeing snow. Most of the rest seeing rain, depicted by the blue imagery there on windy.com. Let's take a look at lightning, and there was some heavy lightning there. A large band stretching all the way from southern Texas up to northern Lake Michigan, really. We had some severe thunderstorms right near Galveston. And yowzers, that is still some extreme lightning. Check it out. Those are the kind of things to produce damaging hail and winds and water spouts. So that is dag. That is a lot of lightning in the Gulf. Next time you hear thunder, check out lightningmaps.org. You could convince the natives that you're Zeus or something like that by forecasting thunder. If you'd like to look like a horror movie villain, forecast thunder using lightningmaps.org. And look at the lightning here. That could indeed be tornadic activity. I mean, something as basic as the frequency of lightning strikes can tell you a lot about what's going on with a storm. So if you want a quick overview of what's happening, again, lightningmaps.org, powered by blitzachtung.org, which brings us to our final segments. U.S. Doppler radar is where we are next. And there's not a lot going on in Alaska and Hawaii. And as usual, we will focus on the lower 48. Here is clouds and fog over the lower 48. Strong band of clouds there stretching all the way from Galveston to Lake Huron and beyond into Canada. And there's the water vapor map. And we're gonna see some continued severe weather here as there's being an impulse. There's a sandwiching happening. So you've got relative low pressure colliding with relative high pressure. You've got an impulse over here. You've got an impulse down here. And where those L's are, there's going to be lots of compression happening there. Also some cold air making some interactions here from Canada. Lots of stuff going on there. Just crossing the Mississippi Valley is all that moisture. Here's your recap. Vertical motion in the air column, represented by the Doppler radar ground-based systems. And now space-based systems depicting 3.9 micrometer infrared radiation and 6.19 micrometer infrared radiation showing the water vapor. And that is where we will close things out. By the way, if you enjoy the content, don't forget to press like, subscribe, share, etc. Don't forget to visit our affiliate links. The 420 sale is still going on. I think it's through the day today. The biggest sale until Black Friday. So links below the video to the Hemp Lucid shop. Don't forget to enter the promo code SMASHOMASH on checkout to save some dough. Also, if you are unable or unwilling to support the channel via subscription services or sending us PayPal donations, etc., press like, subscribe, share, and help us out with clicks by heading to smashomash.com, our official homepage, and welcome to the Neo-Renaissance, a reawakening of critical thinking in the realm of things like science. And we're studying heliophysics in depth like we are because of the advancement of cosmology. If you want to support the channel via subscription services, we launched our own subscription services site back in 2019. Back in 2021 in October. Smashomash.com/SmashTeam is the official subscription services site. If you want additional content, become a member of the Smash Team, especially at the gold or silver level. There is also a bronze level that'll cost you $0 per month. Links to the Hemp Lucid shop, the YouTube channel, the Twitter feed, etc., all on the homepage and at smashomash.com/Smash Team. These videos were brought to you in part by the Smash Team, so thanks especially to our Gold Annual paid-up subscribers. We are in the process of doing additional hardware upgrades, so thanks again everybody who tuned in. Congratulations on realizing the channel exists. Frankly, we're surprised. I've been your host, Dan, a.k.a. Smashomash, signing off, and may that solar wind be at your back.